Now we have to move on to the next talk by Soham Chakraborty. He is an assistant professor at TU Delft. He is going to talk about, shared memory concurrency models. Go for it.
Thank you, Marco. Do you hear me clearly? Should I?
Speak up, maybe.
Okay. Now is it clear?
The mic on. Yeah, it is.
Okay.
Oh, yeah. Now better.
Now it is good. Okay. Hi, everyone. My name is Soham Chakraborty from TU Delft, and I will talk about the evolution of shared memory concurrency in the programming languages. No? Doesn't work.
You have to go to view mode.
Oh. Am I in the right position? Okay. Enter full screen. Okay. Thanks. Okay. So, in today's computing, as you know that concurrency is everywhere, from applications, programming languages, to architectures. And particularly with the emergence of the modern multicore hardware, shared memory concurrency has been a dominant programming paradigm. Now, what is shared memory concurrency? So, in this case, there are different processing units are connected via a shared memory, and the data resides in the shared memory locations where the multiple threads can read and write to exchange information among them and to communicate. Now, given this system, a fundamental question has been that what is the possible executions of a concurrent program? Now, this question has been explored in several contexts, beginning with Lamport in 1979, where he answered this question with sequential consistency. So, in sequential consistency, multiple threads executes the shared memory accesses in the order of the way they are specified in the program, and the threads interleave in arbitrary manner. So, overall, whatever the outcome of the program we get here defines the program behavior. Now, in reality, the systems are not that simple. There are intermediate buffers, caches, and complex memory hierarchy between the processing units and the main memory, which actually affect the behavior of concurrent programs. Now, if we consider the overall space in this area, there are some additional behaviors compared to sequential consistency. So, how do we understand that? Suppose we take a program and try to understand that what are the set of possible behaviors. Let's say this is the set of behavior you can get from thread interleaving. However, there are additional program behaviors which are known as relaxed memory behaviors, and these models are overall known as relaxed memory concurrency. So, to understand this, let's look at an example program, and we will use this example throughout the talk. So, let's understand this. In this program, x and y are shared variables initialized to 0, and the program has two concurrently running threads. Okay? In the first thread, variable x is read in a thread local variable a, and then y is written value 1. On the other thread, y is read in b, and if b is non-zero, we write x equal to 1. And for this program, we ask that if at the end of the execution of this program, both A and B equal to 1 can be possible. Now, if we look at the interleaving executions of the program, then we can see these are the possible behaviors. So let's say we take the first behavior, A equal to B equal to 0. Now, it is possible that the read operations in both the threads are executed first, right? So in that case, X reads from the initial value 0, Y reads the value 0 also from the initial locations, and then the write operations takes place. Now, if we go to the second outcome, A equal to 0 and B equal to 1, we can see that if the first thread executes this program, so in this case, X reads the value 0, Y sets the value 1, and then the second thread runs, then Y reads the value 1, and at the end, B is non-zero, so X equal to 1 can be written, right? But if we look at this program, in no interleaving, we can get both A equal to 1 and B equal to 1 as an outcome of this program. Because when A equal to 1 means X equal to 1 has to be executed, which is not possible unless we get here Y equal to 1 to be executed. Okay? However, if we take this program and say we run on different multicore hardware, this outcome is not allowed on x86 machines like Intel processors and so on. However, in PowerPC or ARM processor, this outcome is allowed. So the devices, for example, our smartphones and so on, which uses these processors, there this kind of weak memory behavior is possible. Okay? Now the question is that here we have seen that this is not possible in x86. So we may think that then if we are using the x86 processors, then we will not have such kind of effects for this program. Now, in addition to these processors, compilers also perform some transformations which affect the outcome of the concurrent programs. If we take the earlier program and consider it as compiled by a mainstream compiler, a compiler may look at the access pairs in the first thread, and it finds that they are independent. There is no dependency between them. They are accessing different memory locations. So for some optimization step, what it can do, it can reorder these two accesses, right? And after reordering, it is possible to have an interleaving execution when we are running on x86 or even a sequential consistent processors. We can see that we can first execute Y equal to 1, then run the second thread. So we get the value B equal to 1 here, which writes the value X equal to 1. And then the second thread completes. It comes back to the thread 1, and it gets value both A and B equal to 1 as a weak memory behavior. So because of this compiler transformation, this behavior is also possible in x86 machines. So effectively, all the processors or the machines that we are using, this behavior can be possible to have. Now, considering these overall weak memory behaviors in the underlying compilers and the processors, the programming languages thought to come up with as a first-class primitives as a concurrency in the programming languages. So it was initially done by several threading libraries, but later it became a mainstream part of the programming languages. And the desired properties here, the programming languages wanted to have is first a platform-independent abstraction. So they wanted to propose a concurrency model which will work for different compilers and different architectures. The second property is good programming model. So this should be understandable to the programmers who are writing these programs. And third is supporting optimizations. So we will come into more details, but essentially we don't want to stop any compiler optimization, or we don't want to stop any hardware optimizations if we write a program in a certain form. Now, let's see that how concurrency can affect the program optimizations. So remember this earlier example and consider that we are considering the model as sequential consistency. So in that case, what may happen, we have seen, is that in the original program, sequential consistency does not allow this outcome. But after this reordering, it is possible to see this outcome, which means a compiler, if it performs the read-write reordering, it can introduce a new behavior. And if we look at compiler correctness, this is not correct, because compilers has to be semantic preserving, and it should not introduce any new outcome. So in that case, we say that that sequential consistency does not allow this read-write reordering optimization. Okay? And not only this particular optimization, in sequential consistency, any kind of reordering will be deemed as incorrect, because there it is possible that there exists some program, it will introduce a new behavior, and there will be a bug. So given this situation, there is a research question here that can we define a concurrency model for the programming languages which can provide us both optimization and programmability. So optimization is for performance, programmability is for correctness. Okay? And if you look at this, this is what you get as an outcome in this area. So this is a paper for 2015 which says that despite decades of research, we do not have a good model of concurrency semantics for the programming languages. Okay? So we will see that why it is the case in the next steps. But if you have any questions, then we can discuss now and then proceed to the next steps. Okay? So let's see. So before defining a programming model or a concurrency semantics for the programming languages, we should understand that what is the goal we have for defining such a model. So we set some goals for programmability, efficiency, and feature coverage. So for programmability, we say that it should not create any bogus execution, or in terms of out of thin air executions. We will see what do I mean by that. And it says that it should provide some guarantees for well-synchronized programs. So what it means that suppose we are writing program with locks, and if we have all the shared accesses within the critical sections, then we should not have any complicated problems. Now for the efficiency, what we want is that we want to allow all desired compiler optimizations, which the mainstream compiler are today performing, and we want the efficient hardware mapping of the shared memory primitives from the languages to the architecture ones, okay? So that we don't compromise any performance. And at the same time, we want to handle all the concurrency features which are having in our programming languages. So with this goal, this problem has been addressed starting from quite early time. So the first model in this case, what to my knowledge, is data rest-free concurrency semantics, or DRF0, in 1990. This model actually came up with a very simple but very elegant solution. So it said that the program, if there is a race, then there is a problem. Okay? And what is a race? If there are concurrent accesses on the same memory location, and at least one of them is a write operation, then it is possible that this program can be buggy. So once we try to understand that how we can get rid of this, the model actually differentiates between two types of variables. One is a data variable, and another is a synchronization variable. Now, for example, if we go back to the earlier program, we can say that X is a data variable, which is kind of, you can think that it is like preparing data in a thread, and which information it wants to communicate to the other thread for computation. And the synchronization variables are kind of flag variables, which tries to signal the other thread that the data is ready, now you can consume it. Okay? Now, it says, the model says that race is unavoidable because we have to communicate, so there should be some accesses on the same memory location. But races on synchronization variable is all fine. We can have data races on those variables, but if we have races on the data variables, it will be an undefined behavior. Means there is no guarantee the semantics will provide for those particular executions. And now, if we look at this particular program, we can see that if y is a synchronization variable, it can be used to communicate this information without any data race on variable x. And based on this model, this has been a foundational model for the modern concurrency semantics for the programming languages. So this model was extended in Java to define a semantic model, and the first model in Java memory model came in 1996. But it was found that it is not agreeing to all the optimizations which are performed in the then JVM hotspot compiler. So the model in 2000, they found that the model is broken. And there were efforts to fix this model, and the second version of the model was proposed in 2005. But again, in 2008, it was found to be broken, because it was again not supporting some of the optimizations and guarantees what the programming language wanted to give. After that, there are several propositions to fix the model, which should give, the idea is that it should give, if you remember, all the semantic goals, the programmability, optimizations, and feature coverage, which was difficult to achieve. And so far, with the fundamental models, there is no solution to this particular idea. So in the concurrent world, people started thinking of defining, yes?
Quick question, are you assuming there is no update to synchronization variables, like they are read-only or what, in the previous example?
This example?
Yeah, what if y is being, or there are updates to synchronization variable as well?
Yeah.
Okay.
Yeah, there are update variables. Here I have gave the example, I simplified the example.
Yeah, in general, okay.
Yes.
Yeah.
So any more questions up to this example?
I see one, two
Okay.
there.
Yeah.
Could you go again the data variables, because I think y also acts as a data variable here, or
So it is up to you to define what is data variable, what is synchronization variable. So the programmer defines a set of data variables, a set of synchronization variables, and write the program.
okay, that answers. Thanks.
Yeah.
So then the guarantee of race freedom is parametric on this choice of data variables and synchronization. Okay.
Yes. Okay.
Great, gone.
Okay. So it was found that along with Java, C++ also tried to come up with a concurrency model as a first-class primitive. So it defined a bunch of memory access with the memory operations. It defined that there are 4 types of memory operations we will perform in C++, which is read, write, atomic update, and fence operations. And they also defined a list of memory orders, which decides that the strength of these accesses for the synchronization. Okay? So, and then it started drafting this model, and then in 2008, the initial draft came in as the first concurrency model. And in 2011, the draft was finalized with several iterations, with the discussion with the researchers in semantic world. And it was finally, it was a mathematical formalization was released in the same year, in 2011. However, in 2013, people found that the C11 model is too weak, and it does not give the proper guarantees for well-synchronized program by any data race. It does not actually provide any data race freedom guarantees. And in 2015, we could show in a paper that there are many desired compiler optimizations are broken in the C++ concurrency model. Means that the model does not allow those optimizations to be deemed correct, which means that now it is not clear that which optimizations we can perform and which we cannot. Then there was a version was proposed to be fixed, and there were several propositions were actually there to solve this problem. Two of them main propositions were in 2017, it was promising semantics, and also RC11 in the same year. They were trying to solve two different kinds of problems, but they improved the semantic model significantly. In 2019, then we defined another concurrency semantics named weakest MO. The full form is weak event structure. And then there were consequently the more advanced model was proposed to solve this problem. Okay. Now, let me give you that what is the problem here. In C++, this model was actually considering this program and this execution. C++ looks at a program execution as a graph structure. And a graph has events which consist of memory operation, memory location, and value as an event to represent a shared memory access. And then there is some relations between these events, which are represented by edges. The program order represents the memory order, the order of the accesses in each thread, and read from actually combines a write and read operation together to show that how this read has read the value. And after this graph is constructed, it wants to see that if this outcome is possible, and it has some set of consistency constraint to check if this graph is correct. And C++ says that this graph is correct and this behavior is allowed, which we want. However, if you think of just a variation of the program in the first thread, also we say if A equal to 1, then Y equal to 1, along with the second thread. Now, this program should not have any outcome with both A and B equal to 1, because no hardware or compiler optimization can result in this behavior. But C++ says that this behavior is allowed for this particular program, and this behavior is possible. And this is where C++ model is actually being very weak for two reasons. It allows some behavior which is not possible in a program, which is termed as out of thin air behavior. And for the LBDEP program, there is no data race, but C++ says that there is a possibility of data race. Yes?
So just to clarify, it's not that we will get the behavior of A equals B equals 1, it's that this C++ analysis is going to lie to us and tell us that B equals B equals 1 is possible?
Yes, exactly. So the model is the weak one. And the deep problem is that once this is for one example, but in general, this does not give any guarantee. That's the main challenge. Now, what actually people notice that these kind of errors are happening because there is a cycle in this graph between the program order and read from edges, right? Now, next, there are some memory models like RC11, which actually said that such kind of cycles are not allowed. Now, what is the effect of it is that in this case, if we have to forbid this cycle, now we have to say that this behavior is also not possible in this first LB program, which earlier we wanted to be possible. Now, the implication is that now the compiler should not perform this read-write reordering. In the architecture level also, we have to stop it. For that, we can introduce some fences when we map this program to the architecture, or in the architecture level, we have to stop this pipelining and so on. So this problem has been solved in several other ways. I will not go to them for the interest of time, but there has been many challenges in this area which has been addressed in the model, and there are new properties which were actually came up, which the programming languages want today. And the C11 model has been expanded to many other languages, including the GPU programming, OpenCL, CUDA, and so on, where what we want is that to model the shared memory concurrency for the GPU programs, which is a new area. And here what we want that the threading model and the execution model is very different, but they also show the relaxed memory behaviors. And more specifically, in today, there are emerging heterogeneous architectures which have shared memory between the CPUs and GPUs. And the question is that what is the model of this kind of architecture and going to be for their programming languages? So quickly, if we just look at this particular architecture and this same program, suppose that we have a processor x86 and PTX are connected through shared memory, then for the CPU-GPU architecture, what will be the behavior if the threads are scheduled in different types of processors? So this is a question which I am investigating with some of my collaborators, which I find quite interesting. And basically, this raises several new research questions that how we can combine different memory models into one, what are the compositionality properties we can have, and what kind of separate compilation we can guarantee there. So to conclude, in this area, what I find most interesting and challenging is that it connects various concepts from PL, compilers, and architectures, and it has a very nice combination of theoretical problems with very much practical applications. So what I could not discuss in this topic is it's a diverse field with many important research which I could not talk about. I could not talk about the program correctness, compiler correctness. There are many work is going on. So if you are interested, we can discuss it after the talk or anytime I am here in this for this week. So feel free to talk to me. And with this, I conclude my talk. Thank you, and I will be happy to take any question.
Okay, we have time for 1 or 2 questions while Aslan sets up. Yeah.
So you talked about how to think about these models, and then you also talked about how people keep refining these models because they keep discovering bugs. But at the same time, one also has to sort of ground it with what the compiler actually implements. So how do we do that?
So basically, the compilers, when the models, basically we try to not to stop any compiler optimizations. The goal is that the optimizations which are written in the compiler, restricting them, first of all, is not desirable. Second, it is very buggy. So what we want to do is that allow these optimizations and then relax the model or change the model in such a way that the overall requirements are met.
But I come up with some model, and then it may not even reflect what the compiler is actually doing. How do we bridge this gap?
So in that case, first of all, that we try to prove the correctness of the compiler transformations. And if we find that it is not allowing this transformation, we have to either relax it or go back to the compiler and restrict those optimizations.
So it's like an iterative process.
It's an iterative process.
Oh, one more question there.
With regards to compiler optimization, you cannot move around instructions. But what if it's a non-concurrent program? Like, how does the compile, like in terms of what a compiler can view, it might not know that if it's a concurrent program or not. Like a function, like if you consider just a function call, so in that scope, it does not understand that it's a concurrent or not concurrent, and it might be called in a concurrent function. So in that aspect, why is it that such transformations are wrong, but they are correct in its own scope, right, or its own semantics?
This is exactly what we want. The compiler need not to know the entire program. The compiler should know only on its scope, maybe at the function level, and it does not know what are the other codes are running in concurrent with this particular code. So the semantic model and the compiler correctness results, which we prove, considers that there exists any arbitrary context on which this transformation has to be correct.
Okay.
So that's how it is proved, and compiler should remain that way. It should not look at the entire.
Okay, thank you.
So that's a requirement.
Great. Let's thank Soham again.
Thank you.